We have quickly grown accustomed to using generative AI tools to write code and to develop software. That is because they are so good at writing code that at least looks like something that will work correctly, and it usually does. There are a few problems though when it comes to doing the software development as a whole. And that is precisely the problem I want to tackle in this video. So here's the thing. It seems like we cannot just leave generative AI tools to develop software on their own. There must be a human in the loop. And I will go one step further. I will say that generative AI as we have it today is a good tool for coding, but the wrong tool for software development. If you are willing to tackle the hype, then in this video I will show you how deep this rabbit hole goes. So to understand how tools such as Claude Code or Codex or any other similar tool work, we need to understand one factual thing, that is that all those tools, with no exceptions, are based on an underlying LLM. They will do that in iterations, they will refine the answers, but the underlying fact is that there will always be queries on an LLM. So to understand, again, how they fail and why they fail, we need to see how the underlying LLM works. LLM is not a monolithic model. There are several large blocks, as you can see on this picture, and each of these blocks required years of refinement and scientific work to get right. It all begins with a tokenizer and embedding, which turn human readable text into just numbers. Then comes the famous attention layer. The attention layer is what made this entire technology work. Without it, it was impossible to make LLMs as we know them today. So let's look into that. The attention layer, it is enriching the text with the meanings of words. That is precisely what earlier models lacked, and so they were not so good. You can see that if you compare Google Translate today with what it was at the beginnings. At the beginnings it was a recurrent neural network. And recurrent neural network didn't have the attention layer, and what happened was that it somehow forgets the meanings of words that happened earlier in the sentence as it progresses towards the end of the sentence. So if you gave it a longer text, it would quickly get confused. The output of the attention layer is what gets normalized and fed into the deep neural network that follows. The actual output we see is the result of decoding that output of the deep neural network. And this is basically the structure of an LLM. And there are the tools around them that use these blocks to produce meaningful, human-readable text. Then came one wonderful idea, the dropout principle. Both in the attention layer and in the neural network, we would randomly zero out a percentage of node outputs to prevent both the attention layer and the network from fixating too heavily on certain words. That is a part of the training process, the network training process, which prevents overfitting. Literally learning the training input and reproducing it on the output. What we want to have from a deep neural network and an LLM is usually referred to as generalization. We want it to find what's common in the input, in the training inputs, so that when you vary that input a little during the use of an LLM, it still generates a reasonable output. It doesn't flip. Now, why do you need to know all this when using Claude Code or Codex? It's because it is the LLM that looks like it has reason. All current LLMs work on these principles, and they really make LLMs look like magic, like they understand what they are telling. But the trick in understanding the technology is in knowing that there is no understanding inside an LLM. There is no reasoning inside of it. And then the outer tools like Claude Code and Codex come into view again. What do they send to the LLM? They send the context window. That's how we call it. That is the prompt you wrote plus the entire conversation packed into one sequence of tokens. That is what the tool sends to an LLM. The term context window first came from LLMs themselves. That is what an LLM accepts on its input, and there is a predefined maximum size of the context window. But then come the issues every programmer must understand. What happens if we start to enlarge this context? First off, larger contexts are progressively more complex to calculate, but there is one much worse effect. As we enlarge the context, the error rates of the LLM start to grow significantly. While the error rate on a small context might be a reasonable 2, 3, 5%, a much larger context would drive it to 20, 30, 50%, making the LLM completely useless. There are perfect mathematical reasons for this behavior, and I'm not going to discuss them in this video. But you need to keep these effects in mind all the time. So we are ready to get back to discussing how AI tools work with LLMs now that we know all this about how LLMs work. The tool is responsible to manage the context window on its end. The context window within the tool must not grow larger than what LLM has fixed. That is the maximum number of tokens an LLM can take in one calculation. And so Claude Code lets you inspect and manage the context window explicitly. Now you understand it. That is the precise explanation of the context window inside Claude Code. It will even automatically compact the context window when it is full, because it is impossible to go beyond the fixed size of it. And because the output of the LLM degrades with the growing context window, the Claude Code documentation advises us to use compacting and clearing to improve the correctness of its output. Writing code is a local problem. That is exactly what LLMs and deep neural networks do the best. So we understand why LLM-based AI tools can write good code. That's what deep neural networks do. But will they develop software? That is not a local problem anymore. Will they do that? That is the question. There are several effects we must notice when we move from coding to software development. The first issue is the context explosion problem. The surface expands rapidly and enormously compared to just developing code in one file, for example. The attention layer and the attention mechanism dilutes very quickly, and that is why the tools are running RAGs, code graphing. They seek consensus by querying the LLM multiple times in smaller chunks. That's why all those mechanisms are at work, because it's not possible to grasp the entire problem of developing one entire feature in a software product at once. And then people say, whenever I point out that LLMs and tools around them start making mistakes in that mode, they say, why don't you give precise instructions? Well, that would be very easy. Just type, 500 or 1000 pages of text and let the AI tool work on that. Sorry, that's not possible, because it is much larger than the context window. That's the hard limit. So what tools do is to split that knowledge into tools, into skills, into smaller markdown files that they selectively pick and read and put into the context. But you understand, there is a fundamental problem with that, because the LLM always makes mistakes at a certain level. Make it 3%, 5%, that's fine. We can live with that. But if you let the tool run in numerous iterations, those mistakes start piling up. And then when you look at what an autonomous tool did in a large feature development, you will find the whole bunch of architectural and design mistakes it made. Now the question is whether you want to tolerate that or not. Many people say code doesn't matter anymore, it's not important as it was. That is wrong. That is very wrong, because if you let those mistakes start accumulating in your project, the code, the entire code base you are developing will at some point start exhibiting instability at runtime and inability to add more features at some point. That is a very important problem we must keep in mind. And that is why I say that maybe we should actually face the truth instead of force-fitting generative AI into every task. Maybe just we should accept that LLM-backed generative AI tools we have today are excellent at coding, but not so good at software development. They are good at localized tasks, such as writing a piece of code inside a file. That is a local task, they excel at that. They are not good at developing a feature or numerous features or doing the entire architecture across many files. They dilute their attention, they lose their accuracy, the error rates grow wild, and that just produces problems in software. We experts in software development must stay in the loop and make the LLMs correct those mistakes at the same time when those happen. We must not leave them work without attention of a human expert.